about the quadratic function, we will see, I think, no less than 50 times, 50, okay? So if you get surprised now, you know, after a while you get to practice and you immediately see this is a quadratic form. Now, so that means that since we will see the quadratic form many times, it's a mathematical formulation that we need to learn how to manipulate, how to handle. Okay, so which means that, you know, in order to understand about the quadratic form, we need to put our mathematical hat. And now we need to see, okay, let's see what are the properties. Now, the reason for that is because we can make this procedure in a self-learning way. What is a self-learning way? Which means that, you know, in this quadratic form is similar to a ball like this, okay, shape. And, you know, our axis, you know, will be, this is theta 1, this is theta 2. This block is for p equal 2, which means 2 dimension, okay? And the third dimension is j of theta. Now, this illustration is only for p equal 2. But if we are working, as is commonly the case, with the dimensionality, that is, I don't know, 3, 4, 5, p equal 20, 30, 55, and so on, so that means that I cannot represent graphically, okay? But conceptually it is the same. So now, you know, sometimes what I can do is that I want to learn the configuration of the data such that I can predict the value of the stocks. Okay, we start with the stocks, but, you know, it can be valid for anything. I can work in an iterative fashion, which means that, you know, I might start with a set of value here, which is theta 1 at iteration 1, and theta 2 at iteration 1. Okay, and what I can do is that I can start from this point here, and then I can use the iterative method to solve and to find the minimum. Now the minimum is here. Okay, so this value is theta optimum. It's optimum because it's minimizing that. Don't forget, our goal is to minimize j. Okay? So that's our goal. So since I want to minimize that, I want to go there. Okay? So I can work in an iterative fashion. Iterative fashion is the common learning method for this kind of system. Now, how is it? Graphically. I do it graphically and mathematically. Okay? So I do both ways. How do I make it graphical? Okay, graphically means when I start from here, I want to go there, right? So when I'm here, I want to go to the bottom. How can I go to the bottom? You know, I need to calculate something. And this something is the gradient. So the gradient of this function is giving to me the direction. This is the gradient of j with respect to theta. Okay? This gradient is giving the direction where the surface is maximally going up. Okay? So if this one is a gradient, then what I can do is I do the opposite of the gradient. So this is minus gradient of theta, which is going down. So minus gradient is going down, and then what I do the following. I just, you know, update my position with the gradient. This is iterative method, or, you know, it's a self-learning procedure. So how is it? The way it is the following, you know, is I start from a certain point, and my theta at iteration I plus 1. Now this iteration may be new data, this iteration may be a learning iteration, this can be a piece of code which goes in the computer, Okay, it doesn't matter. So doesn't matter means it doesn't matter in the way it is implemented. Huh? But conceptually, this means that I update my theta such that the theta I plus 1, so the new theta, is equal to the old theta minus. Now minus is because I'm going opposite direction to the growing path. Okay, because the gradient is going up. I take a minus because I'm going down, and then this new is so-called the step size. Okay, or learning wave. Now, so I mean, this is this is the formula, which is how I update. So how I move down. See? Okay, now let's consider a very simple case where I have just one data. So the total number of data is 1, capital N. So my total data, I will go to Yahoo and I have just one sample. Okay? Let's make this example. Now, assuming to have one sample. Now, I can calculate the gradient. Okay? Now, how is the gradient? The gradient of what? Okay, the gradient is if I don't have samples, the sum goes away. Okay? So this is there will be the sum of theta transpose multiplied by xn, but since I have one sample, I have just one. Okay? Minus y1. Okay? So now I need to calculate the gradient. Now, gradient is a derivative. Okay? Gradient is just a derivative with respect to each of these entries. So the gradient is with respect to theta. Now, when I write it this way, gradient with respect to theta means that I'm calculating the partial derivative with respect to each entry, each variable. In other words, if I write here the gradient with respect to theta I vector is equivalent to write the gradient with respect to theta I1. How did I indicate? The gradient with respect to theta 2 at iteration I, and so on. Until I have the gradient with respect to theta p at iteration I. Okay? So that means that the gradient is a p-dimensional vector, because the gradient is the derivative with respect to each of the entries. Okay? So this is p times 1 vector. Okay? So when I ask to calculate the gradient, then I have a gradient with respect to p. Now, this is a square. So if I have a square, when I calculate the gradient, these two goes away. So these two goes here. And these simplify with 1 half. Okay? So when I calculate the gradient, it is 2 times, and then it is this entry, and then the gradient with respect to the value's internal value. So it is 2 times, simplify with this, and then I have the external value, then the derivative with respect to the inner part. Now, so let's look at here. How this is written. Now, the gradient with respect to theta of y1, this is a number. So the derivative with respect to something of a number is 0. Okay? So this gradient with respect to y1 is 0. So the only which is left, is the derivative, so the gradient with respect to vector theta I of theta transpose x1. Now, since this is a scalar, so I need to write the corresponding scalar. So the gradient now is the gradient of the sum of terms with respect to theta I. Now let's do it here. Now that one, let's write here. Let's write here. So it remains to you. what I'm computing now is this part. Yeah. This is what I'm computing, okay? Now in order to compute this, okay, as I wrote, this is equal to, you know, it is the derivative of theta 1 of the sum, which is sum of L equal 1 to P theta L x L 1. Derivative of with respect to theta 2 of the same sum.
No, l'abbiamo portata
giù, scusate.
Theta P of the same. Okay. Then everything has to be calculated for theta equal theta I, because you know it's I iteration. And this is what is written there. So now, you know, if I look at the first, if this is the sum, the first one, it's the sum of theta 1 x1 plus theta 2 x2 plus theta 3 x3, but you know, I have a theta 1. So the only terms that remains here is the derivative with respect to theta 1 of theta 1 x1, which is x1. Okay? So this one is x1. x1, 1. About the second one. The second one is theta 1 x1 plus theta 2 x2, and then I need to calculate the derivative with respect to theta 2. Then the only that remains is x2. Blah 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 up to the end. So the last one is the only term that remains is xt. Okay? So the output, the final result is this vector, which is this vector is x1. Okay? Clear? Oh, let's go. So this is the reason why, you know, this is giving this x1. Okay? So it has, you know, quite a nice compact form at the end of the story. So now, I mean, my up-to-date formula, okay, is don't be confused. Since I have a minus here, the minus is cancelled by flipping this term. You see, I have theta x minus y1. I put y1 minus x there. Okay, so I simply flip it. So this is my up-to-date formula. Okay. So this is how the update has been. Let me write this way. This is how is it modified. Okay, very compact. Now, so the modification is made in such a way that, you know, this is the error, okay, which I indicated epsilon 1. That depends on theta. Okay, and so this error, since depends on theta, depends on the theta iteration I. So it's theta. Okay, that's, you know, that's the result of this stage. Now, different way to update this formula. Okay, assume now that I have n training data. Okay, so my training is much longer. I have the training data for all the stops, not just one day. So I can make two different ways to calculate the update. One is by the so-called considered batch gradient. The batch gradient is very simple. I repeat, okay, by summing all the terms. You see now, I take the formula before, and I am simply introducing this sum, because I'm summing with all the n terms. So, you know, the formula is the following. I iterate with theta until I reach the convergence. So, which means that the gradient is batch, because I compute the gradient by using all and training. So I take all the training, compute the gradient, make a step. All the day training, compute the gradient, make a step. Okay, this is why it's called batch. Okay. The other, you know, is incremental, or sometimes called stochastic. Okay. Now the incremental is the following. You know, every time I have a new samples, and here, when I compute the gradient, I use one sample of the data. So I take one sample, I correct. Then I take two samples, I correct. Take the third samples, I correct, and so on. I keep going this way. So I make a 4. So for n equal 1 to capital N, which means make a 4 with all the data. Of what? Of the update formula, same gradient, okay? I make a 1 update steps for every iteration and for every new training data, or for every training data. And then I repeat all of that till convergence. So this means that in the second part, the step size is, you know, is controlling, basically, is controlling how long is my step, which means if I am in this position and I'm calculating the gradient is changing sign, so I change the sign to the gradient is telling to me in this direction, to go in this direction. Okay? Now, how long I make my step? My step is made very long, okay, because if I'm very confident on the quality of the gradient. If I'm not confident on the quality of the gradient, I make a smaller step. So, in the first case, the gradient is computed by averaging all the possible gradient. Then I can make a longer step. In the second case, you know, I make a shorter steps because I am not confident on the accuracy of every gradient that I compute. Because the gradient is computed with one sample and not with all of it. Now, we will see that these techniques are part of the so-called adaptive filtering. Adaptive filtering is a filter that is using some data known, which is called training data, in order to estimate the filter itself and apply the filter on the data. Typically, in the adaptive filtering, it's used the second approach rather than the first. Because the second is, you know, is a start using the data, you know, when the data are entering into your computer, your calculator, your microprocessor, your DSP processor. So you start computing. On the other hand, you need to wait until all your data has been computed, then you make a step. Okay? So if you can imagine going ski, okay, if you ski and you want to go here, and because here there is a bombardino, you know, so you know you want to go to the bottom of the valley. If you want to go to the bottom of the valley, then you have two options. One is that you start moving, but you don't trust that much. So you might be on a small valley, but then you know there is a stone, so you don't trust anything. So you start moving. This is the second option. The option on the batch is the following: you want to ski, and before skiing, you study all the situation. You acquire as much information as possible. You look around. The other guy keeps going, and you are there. Okay? You are there looking, and then you make a step. Then you stop. And then again, you look around, you evaluate the gradient, you make a step. Okay? There are two different approaches. So one is called, incremental or stochastic gradient. The reason for stochastic will appear, after. And the first one is a batch. Okay. Now let's rewrite. Okay. The entire problem now. This one. Okay. Let's rewrite the entire problem having to do with all the n samples by using, all the data and derive in this way the so-called normal equations. Still solving the problem. Remember, we need to gain money, okay, by stars. I would say a very practical problem. Now, I can write the errors. So every entry, every one here is the error. So this one is error at iteration 1 given theta, because its theta is unknown, my theta vector. The second is error at the sample 2 given theta, and so forth. Epsilon at sample n given theta. Don't be confused with theta. This theta writing is only to remember as a mnemonic to remember that everything depends on theta. So theta is my unknown. Okay? So I can organize all my into a vector. Okay? Now this vector is written in extensive form in this way. So, it is theta t transpose multiplied by x1 minus y1. Okay. Now what I can do is I can rewrite this formula by using some basics of the algebra. Rather than writing this way, it's a scalar. So since it is a scalar, I can make a transpose of a scalar. So this is the same as having x1 transpose multiplied by theta. Same, no? Because it's a row time column, so I can make a row time column, right? So it's a scalar. Okay? Now there is a convenience to make it this way, because if I write this way, then I can write it the way the second formula there. Why? Very easy. The second formula is illustrating the following. So it is x1 transpose, x2 transpose, 2 transpose, x and transpose. Okay? So this means that these are row vectors. Because if x is a vector, x transpose is a row vector along the row. Okay? Then I multiply by theta, external theta. Now what is this? This one is a set of numbers multiplied by column here. The length is p. So this one is x1 multiplied by theta 1. Okay? So it is x1 transpose theta. x2 transpose multiplied by theta. And so on. So which means that one can be rewritten more conveniently in this way. This is the vector. But this matrix is important because this big matrix is containing all my training data. Into a matrix I collected all my training data. So this big matrix X has a size, which is n times p, contains all the trainings. Okay. Now, if n, n is how many days? Now those data were 4 years, 5 years. So it's 250 days, because the weekends are out. So that is 250 days, 4 times 4 years. So in that case, it is 1,000 times, depends, I don't know, if we use 6 parameters, it's 1,000 times 5 times 6, okay? Just to give a number, okay? So that one is 1,000 times 6, okay? Just to give you an idea, what are the size of the problem that we are manipulating now. Okay, so this is equivalent to this representation. And then I collect all the y. So y1, y2, blah, 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 and this is the vector. Okay. So this one can be rewritten in a very compact way, equal capital X multiplied by theta vector minus y vector. Okay. So if I need to compute the error, remember, if you like, this is the vector epsilon that depends on theta. Okay. So the quadratic form, here, right here. So the quadratic form, the problem itself, is a j of theta, which is epsilon theta vector transpose epsilon theta. So this is my objective, with all together, putting all together. Okay. So since epsilon is this one, I copy this epsilon. I copy this epsilon there, and I copy this epsilon there. Okay. Sometimes it is more conveniently indicated as the L2 norm of the vector, because epsilon is a vector. Okay. So it's the norm of the vector epsilon, which depends on theta. So this one, is a norm of the vector. Now, once again, the cost function can be grouped now. This is similar to the one that we wrote before on the top, okay? But it's only derived in a slightly different way, by manipulating matrices. By the way, we will manipulate a lot of matrices. Okay? So if matrix is against your region, you're better to change, probably the faculty. Okay? Because there is an intrinsic reason about the matrices. 20 years ago, manipulating matrices by software, by hardware, by computers, by system, when I say computers means, the computers that work in the banks, okay? So manipulating matrices was very inconvenient and very difficult, and was, not common. So for this reason, the size of the data were very limited. Now the size of the data is getting very big data, okay? So the size of the data is getting very big. For this reason, okay, now means 2018, 2015, the last 3-4 years, okay? I would say that getting involved or being a little bit with a good manuality with the algebra is a plus. It's something that you must have. This is why I say, it's better you change totally discipline. Okay? Because that's the way. The world is going this way. So anyway, so I can replicate the same analysis that I did. So I can take this, multiply by that, and make it transpose, blah, 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 blah. This is what comes out. So what comes out, again, is the quadratic form on the top, where I indicated this as J0. Okay. The J0 is the sum of y squared. In fact, this is a vector y times a vector y. And then when I make, when I calculate, it's the sum of this multiplied by that, and it is the sum of square, right? So there is no difference on what is written there or what is written here. It's only derived in a different way, okay? But the way you derive is your option. You can use whatever you like. But, the way the reality is, it is, okay? So at the end of the story, our formula, which is describing what I need to minimize, is this one. You see, up to now I've been fooling around how to minimize, but I never minimized. Okay? Notice that, because I know that you want to get the results, but I don't give you the results. I want to see how much reasoning we can do on that. I want that you get practice on the tools, and you don't realize, but we have been touching now the product of vector, the inner product, the outer product. We are revising algebra. We are looking at the possibility of making the derivative. So there are many items that we are, hiddenly revising, which is less boring than revising algebra. This is the formula, and this is the other. Okay. This was the goal of today. Anyway, so let's compute this optimum. At the end of that, we need to know how much money we want to gain from these stocks. Okay, so the way to compute is we have a scalar, which is J. The J is the one here. Okay, so we have this scalar we want to minimize. That is the J theta there, or the one which is in the previous page. We want to calculate the derivative of J with respect to theta. Now, if we want to calculate the gradient, we need to, in order to calculate the minimum of a multivariable case is the gradient and set the gradient to 0. Okay. So I take and I put to 0 the gradient with respect to J. And in order to calculate the gradient, I need to calculate, it's a sum of 3 terms. So I need to calculate the gradient with respect to the first. The gradient with respect to, where is it? Here. The gradient with respect to the first. The gradient with respect to the second. The gradient with respect to the third, but this is 0. Okay? And then R equals 0. So I impose. Okay. So I impose that to get the 0, to get the minimum. Now, how can I calculate that? Now, in order to calculate, I give you the result. Okay? And now every time now I make a reference to the formula, I make a reference to the book because I use this one. Okay? So I go to the book, and then I go to page section 1.4, and then I say, okay, this is, perhaps I say, I remember something similar. Let me go some books. I go to Google and I say, okay, quadratic forms, derivative of quadratic forms, gradient with respect to quadratic form. Let's see. And then I can find these formulas. So I put inside, and then I get that theta. Okay, it is r multiplied by theta is equal to okay. So then theta. Now, in order to indicate the one that I'm searching, I use head. Okay. Now the head is my search value. Or the estimated value. Okay? And this is equal to r to the minus 1 times p. Now I remember what is r. Since r, okay, is x transpose x, and since p is x transpose y, so I plug in and I get this one that are called the normal equations. So the normal equations are simply the estimated theta, which is the theta that is let me gain money based on the trained data. Okay, so the learn structure is equal to x transpose x, which means the total set of data. Okay, x transpose x to the minus 1, the big matrix. Okay, so since x, just to see, you know, since x is n times p, this x transpose is p times n. This x is n times p, so this one is p times p. Okay? So this one is p times p, and then you know I need to make an inversion of a p times p matrix. So p is 6. It's not 1,000. That would be the trouble. Huh? So this is the solution to get rich. See? To predict it. Okay, from the data. Now, there is something that which touched, and we really, you know, what is the derivative rules. Now, let me read that. Let me revise that. Okay. Now, we need to study a little bit how to handle the matrix derivative rules. These are, you know, standard rules. Now, I mean, these last 5 minutes is mathematics oriented. Okay? So, assume that I have a vector. Now, these mathematics, these matrix derivative rules are nothing to do. So the notation is x, so it's x is any vector. Okay. So now assume that you have a vector, and this vector is composed by n entry. So I can make a mapping between n to 1. This n to 1 is a function. So that means that every time I have a vector, I can map n values into 1. This can be summarized as phi over x, x bold, which is x vector, which is equivalent to a function phi that depends on x1, x2, and x. Okay? So it's a function of n variables. Okay? So the n to 1 mapping is a function of n variables. Now, I can calculate the gradient. Now, the gradient is, is the gradient with respect to a vector. Now, this notation is a notation that I used before, okay? So I simply put the notation table without discussing. But, I deserve a little bit of reasoning now. So, I need to discuss about the derivative of a scalar function with respect to a vector. Now, this one that I'm indicating is a notation. Notation indicates that this one is the partial derivative of a scalar function phi that depends on the set of variables with respect to vector x, which makes no sense if you think about it. But this is a notation which says that I need to calculate the partial derivative for each entry that are composing the function phi x. So I'm calculating the vector, which is the derivative with respect to x1, x2, blah blah, and okay. So this derivative is giving a vector that has a size n in response, as a result, to the mapping n to 1. Now, I can also take the other option, which is assume that I have a function which is not just a function, but it is a multidimensional function. This one is, is a matrix. It's a vector. It's a row vector. A row vector contains a function 1 that depends on the set of variable x, function 2 that depends on the set of variable x, function n that depends on the set of variable x. When I write the partial derivative, so the gradient, with respect to a vector of a vector, that's another notation. Okay? This gradient is the gradient for every function. This gives the matrix of gradients. Now, let's make a case. And this is another extension. Let's make a case. Calculate the derivative with respect to x of a function phi x. Phi x is x transpose a, or, which is the same, a transpose x. Okay? Now, the derivative with respect to x of x transpose a, since it is x1, a1, x2, a2, x3, a3, when I calculate the derivative with respect to x1, the only remains is a1. When I calculate the derivative with respect to x2, the only remains is a2, and so on. So for this reason, the derivative of x transpose a with respect to x is equal to a vector a. Now there are some special cases. For instance, if I calculate the partial derivative of the gradient with respect to x of x transpose is equal to the unit vector. We discussed this one later. Suppose now that I have x transpose ax. This one is exactly the quadratic function. Okay? The quadratic function, just to remember, the quadratic function is something that contains, is x1 square, x1, x2, x2 square, x1, x2, x3, x1, x4. So all the products. Okay? This is quadratic function. If you forgot, okay? A quadratic function is a11 x1 square plus a12 x1 x2 plus a13 x1 x3 plus a22 x2 square plus, you see? This is a quadratic function, okay? I know, but just to refresh. Okay, so this, if I want to calculate the derivative here, it's obvious. If I calculate the derivative with respect to x1, the only remains is this one. So the derivative is 2 times a11 x1. This one is a12 x2, because x1 is going away. This one is a13 x3, and blah blah blah. Okay? So I can use the formula that I did, and I can say that if I need to calculate the gradient with respect to x1 transpose ax, what I do when I have a product, I can keep one term fixed and calculate the derivative of the second. Or I can keep the second fixed and calculate the derivative with respect to the first. Okay, so I can do this way. I keep the first fixed, calculate the derivative with respect to the second, plus the second fixed and calculate the derivative with respect to the first. I use the formula before, blah, 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 and then at the end of the story, okay, at the end of the story, it comes out that the derivative, you can read by yourself, so you have the slide, and it's in the book as well. So the derivative is this one. So the derivative of x transpose ax, the gradient, with respect to x is A plus A transpose multiplied by x. Now, if A is symmetric, a new concept, what is a symmetric matrix? It's a matrix where a typical matrix and a transpose is the same as itself. Now, you can try yourself, test yourself, that the matrix that we have seen is symmetric. So in this case, it comes out that the derivative of x transpose AX, which is the term on the top. So before was, this one was the derivative with respect to theta of theta transpose R theta. That was the problem, okay? And this one is equal to 2 times R theta. This is the result we use. Close for today. Okay?